Good afternoon, everyone. Let's jump right in. So we are still working on hypothesis testing, and that's what we'll see, for the rest of this week. So this is what's finishing out the semester for us. Before I jump into today's example, I thought it would just be a good idea to run through the different scenarios that could come up with hypothesis testing so that you are able to identify which approach to follow. And so let's do that. First thing you should pay attention to is what keywords do you see? And this is going to be one of two things. It's either going to direct you to tests dealing with a percentage or a proportion, or it's going to direct you to a test dealing with a mean or an average. So when you're reading a problem, identify which one of those two sides it fits into. What we are doing at the moment, it will only be one of the two. So that's step one. If you've identified that it's a proportion, then you know that your notation that you're going to use is P represents the population proportion, P hat represents the sample proportion, and P0 represents the hypothesized proportion. And usually your null hypothesis is going to be, well, not usually, always, your null hypothesis will be that P is equal to P0. And your alternative, this is where you have to pay close attention, because the alternative could be not equal to if there's no directional statement, or it could be greater than or less than. And finally, your test statistic here is going to be a z statistic p hat minus p0 over se0, where that se0 you calculate as the square root of p0 q0 over n. And you'll use the normal table to evaluate. Okay, so that's if it's about a percentage or a proportion. If it's about a mean or an average, then your notation is going to be mu represents the population mean, y bar represents the sample mean, and mu naught represents the hypothesized mean. So in this case, your null hypothesis will be that mu is equal to mu naught versus an alternative. And again, depending on how the question is formulated, it could be not equal to, it could be greater than, it could be less than. Now, here there is a fork in the road. Because you have to determine whether the population standard deviation sigma is known. And depending on the answer to this question, you'll follow a different approach. And this will be clear in the formulation of the problem. It will say the underlying population has a standard deviation of 2, or it will say the sample standard deviation is given by a specific number. So if the answer here is yes, then, let me just set this up. If it's yes, then you're going to calculate your standard deviation as sigma over square root of n. Your z-statistic will be y bar minus mu naught over the standard deviation, and you will use the normal table to evaluate. If the answer is no, then remember that S represents your sample standard deviation. If you don't have the population standard deviation, you need the sample standard deviation. And then your standard error is given by S over square root of n. And if you're using sample standard deviation instead of population standard deviation, you no longer calculate a z-statistic, you now calculate a t-statistic. You would have learned about this in the lecture recorded from yesterday. And now you need to use a t-distribution to evaluate your p-value. So the easy distinction is between proportion or mean test. But if you're doing a mean test, you have to pay very, very close attention. Whether sigma is known or whether you have to use S, that is very key in how it plays out. And if you're using a t-distribution, you also need to calculate degrees of freedom. Some days I can still spell. And degrees of freedom are just given by sample size minus 1. And we will look at a couple of examples doing this t-distribution calculation today. But this schematic representation should tell you what you need to know to figure out what test to use. Now, let's move across to our examples for today. And first example we're looking at is just going to deal with calculating quantities related to the t-distribution. And I think because everyone is working from home and not everyone has the same calculator, the easiest resource I found for doing this is actually a website. And so even on the exam, I would recommend bookmarking this website because it really makes t-distribution calculations very, very easy. And that's what we're going to refer to today as well. So when we're working with the t-distribution, let's say we're looking at part A. The subscript 12 here, that represents our degrees of freedom. The degrees of freedom are always just one less than the sample size, but they have a big impact on the calculation. So the t-distribution and the normal distribution have a lot in common because they're both bell-shaped symmetric distributions, but the t-distribution tends to have fatter tails. And what that means is you're more likely to have very large or very small values with a t-distribution relative to a normal distribution. But the larger the degrees of freedom are, the closer you end up to a normal distribution. So the distinction between them disappears as the degrees of freedom increase. And usually when you get to about 50 degrees of freedom, you can no longer tell the difference. But you'll see all of the examples today pretty far from 50 degrees of freedom. But you can still visualize for yourself a bell curve. And the bell curve will always be centered at 0. And then in this example, the first one, our reference value is 1.6. And we're trying to find the P here. Capital P means probability, but that's just shorthand for saying we want to know how much of the T distribution with 12 degrees of freedom lies to the left of that value. That's what the less than or equal to tells us. It tells us which direction we're looking at. So we're trying to find for the T distribution, how much of the distribution did we just shade? So this is where this calculator now becomes very handy. In fact, what I wanted to show you here is if I open my browser and I just Google T calculator, the link that I provided in that first example is the first link that came up on my page. So when you open this, you'll see it says T distribution calculator. It has a little box. You're always just going to complete two of the three quantities. Random variable you'll keep as t-score, and we're trying to evaluate a probability, so you should know you're not filling in that, but you do want to know degrees of freedom and the t-score. So in our first example, the subscript, that's the degrees of freedom, that's 12. Our t-score is 1.6. And then you hit calculate. And in this case, that gives me 0.932. So that calculator always tells me what area to the left is. So it is automatically giving me the shaded region in this case is 0.932. So in this case, direct application of that calculator said the chance, if I know I'm working with a T distribution with 12 degrees of freedom, the chance that I select a random number from that population and that value is less than or equal to 1.6 is 0.932, or of course 93.2%. So that's a very plausible scenario, right? Happens 93.2% of the time. Now let's look at B. This time we're dealing with a T distribution. My zero here looks a bit like a 6. 20 degrees of freedom. And I can visualize my bell curve again. My reference value is 2.5, but this time what you'll see is I'm trying to find the probability that I'm greater than 2.5. So that means I'm trying to find how much of the curve is to the right of the number that I selected, the 2.5. I can still go and use my calculator, but that calculator by default always gives me probability to the left. So I can calculate the probability for a T distribution being less than or equal to 2.5. Right? If I go over to my T calculator here and I enter 20 degrees of freedom and 2.5, let's go ahead and do that. So I'm emptying out the probability. I'm saying 20 degrees of freedom, a t-score of 2.5. That gives me 0.989. So let's go back to our worksheet. And so it's given us area to the left is 0.989. So how much is left on the other side? Well, in total, we have 100%, whereas a proportion, it's 1. So, so this is 0.989. But what I want is the probability of exceeding 2.5, the shaded region. Since the two sides of the bell curve have to add up to 1, I can just take 1 and subtract out this number. And so 1 minus 0.989 gives me 0.011 or 1.1%. So small chance, if I know I have a t-distribution with 20 degrees of freedom, pretty small chance that a random number from that population will be larger than 2.5. And our last example here, part C, we are looking at a t-distribution with 5 degrees of freedom, but this time the probability is asking for us, what's the probability of being between -1 and 3. And let me just shade this region and then I'll look at, let's see, there's a question. So this is what we're trying to calculate in C. So a very good question here. Haley is asking whether or how things are different depending on whether it's less than or equal to. And the short answer is it makes no difference. The equality is just around for technical reasons. So it does not matter whether you say less than or equal to on these t-distribution calculations. Same goes for the normal distribution. So as long as you get the direction right, it's not going to make any difference. So adding or taking away the equality to the less than or equal to, really no big deal here at all. Now back to part C, we're trying to calculate how much of the distribution is between -1 and 3. And we're doing it for a t-distribution with 5 degrees of freedom. So we can go to our t-calculator and do calculations for the two reference numbers that we have, for -1 and for 3. And I think everyone's kind of seen how I do that already. So I'm just going to enter these values on the page that I would get from going over to the distribution. I would say I have 5 degrees of freedom. In fact, if you're wondering, behind the scenes here, I'm doing this on my phone. If you enter 5 degrees of freedom and a t-score of -1, the calculator is going to give you 0.182. If you enter 5 degrees of freedom and you do a t-score of 3, and remember to clear the probability before you hit calculate, this is going to give you 0.985. Now, this is always the part of the curve to the left of the number. So this is telling us to the left of -1, this tail region, that part of the curve represents 0.182. Now, the next number for 3, that gives us everything to the left of -3. So perhaps the most helpful thing to do, there's more than one way to do this calculation, but to me, the most intuitive way is to say, oh, well, how much is then to the right of 3? I know that has to be 1 minus the 0.985 I just calculated, which means it's 0.015. So how much is then left in the middle? Well, I know how much is not in the middle. If I look at what's between -1 and 3, I can just subtract those values from 1, and whatever is left, that's what's in the middle of the distribution. And in this case, that is 0.803 or 80.3%. So bookmark this website. If t-distribution comes up, that's what you will use for the calculations. And number C is just one example to show you, a slightly more complicated scenario. But most of the time, you will have things like A or B where you're just dealing with one side of the curve. But pay attention in all the problems, because the context is going to be given to you each time to figure out how to do the calculation. Now let's go to, before I start the next example, if there are any questions, please feel free to ask those now. Okay, let's look at example 2. A report on healthcare in the United States says that 28% of Americans have experienced times where they haven't been able to afford medical care. A news organization randomly sampled 801 Black Americans, of whom 38% reported that there had been times in the last year where they had not been able to afford medical care. Does this indicate that the problem with access to medical care is more severe among Black Americans? Set up an appropriate hypothesis testing framework and evaluate your conclusion using a 5% evidence level, also known as a level of significance. So first thing, proportion or mean. We are dealing with percentages here, so it's a proportion. And so you want to go and identify, what is your sample proportion? And P on its own denotes your population proportion, and P naught, that represents your hypothesized proportion. Now, in the sample of 801 Black Americans was taken, and in the sample, 38% said they didn't have sufficient access to health care. So the sample proportion is 0.38. The hypothesized proportion will always correspond to what had previously been believed to be true, or the status quo, whatever has been believed to be the truth up to this point. Sorry, I'm mixing up my writing today. So 38% there. Hypothesized proportion, what had previously been believed to be true, was 28%. And we want to now set up our hypothesis testing framework. So our null hypothesis will be that the population proportion maintains the status quo. We had believed there was 28%. We want to determine if it's still 28%. But the alternative, this is where you go and look for a directional statement. Does this indicate that the problem is more severe, increase, larger? That's the key word here. That tells you how to formulate the alternative. It uses the same value as the null hypothesis, but it introduces this directional statement. More severe, in this case, would mean P is larger than what we believe to be true under the null hypothesis. So there's our null and our alternative hypothesis. The other thing we need, if we're doing a proportion test, is we need to calculate SE0. And that is the square root of P0, Q0 over N. P0 is 0.28. Q0 is just the complement of that, so 1 minus 0.28. And we divide by our sample size of 801 and take the square root. And this is 0.016. Now we can calculate our z-score. P hat minus P naught over SE naught. So sample proportion is 0.38, P naught is 0.28, divide by 0.016, and we get a z-score of 6.25. Now, next thing we need is a p-value. P-value requires using the appropriate distribution, and because it's a z-score and because it's a proportion test, we're using the normal distribution as a reference. The reference value we calculated is 6.25, and because our alternative says greater than, we want to know what part of the normal curve is to the right of 6.25. So here you're not going to use the t-calculator, you have to use the normal table, which we've done on more than one occasion. But what you'll find in this case is if you go and look up, or try to look up 6.25 on the normal table, it's going to be completely off the chart. In fact, let me open the normal table to show you. Here's my normal table, and if I go through the normal table, the largest value I have is 3.99. And at 3.99, my value is 0.99997. And you can see that the larger the z-value, like as the z-value increases, this probability also increases. And so the probability is going to be larger than this 0.99997. Sorry, let me get back to this example. So you can approximate it with some number larger than 0.9997, and it still has to be less than 1. So, I mean, you could use 0.9998 or 0.9999, doesn't really matter that much here. That'll be the area to the left, and so to the right, I have 0.0001. Or if I multiply that by 100, it's still 0.01%. That's my p-value. My p-value is 0.0001 or 0.01%. And the problem said use a 5% evidence level. So that is just a threshold that you use to determine whether you should reject or not reject your null hypothesis. You're always going to compare it to the desired evidence level or the level of significance, LOS for level of significance, and the p-value is less than the evidence level. So that means we have a small p-value, because small or large is always determined relative to the level of significance. But a small p-value means you are going to reject the null hypothesis. What does it mean if we reject the null hypothesis? Well, that means that the truth, or the sample evidence at least, suggests the alternative is true. So you will write a conclusion that says something to the effect of sample evidence is consistent with the alternative hypothesis, which says more than 28% of Black Americans at times have had inadequate access to health care. So always remember to go back to, whether you're rejecting or not rejecting, go back to the null or the alternative and formulate a sentence around that to give interpretation to the conclusion that you reach. Are there any questions about this example? Okay, then let's look at number 3. Textbook authors must be careful that the reading level of their book is appropriate for a target audience. One way to assess that is by looking at the average word length. So there's our keyword, average, or mean word length. That immediately tells you this is a test about a mean or an average. Right? We take a sample of 20 words from a randomly selected page in our book, count the number of letters in each word. For this sample, that's important again. For the sample, we're given an average and we're given a standard deviation. That pertains specifically to the sample. So we are being given sample average is 5.5. Sample standard deviation is 2.69. Are we ever told what the population standard deviation is? No, that's never mentioned in this problem. So we are doing a test for a mean using the sample standard deviation, not the population standard deviation. So this will be a problem that uses the T procedure. That's the correct approach to follow here. Now let's set up our null and our alternative hypothesis. Let's just read the last part of the problem. Suppose that the editor was hoping that the book would have a mean word length of 6.5 letters. Does the sample indicate that the authors failed to meet this goal? So the hypothesized value, their goal, what they were hoping to be true, was that the mean would be 6.5. Is the alternative in a specific direction here? No. We are just told failed to meet. So our alternative is two-sided. Mu is not equal to 6.5. That's what our alternative looks like here. Now, we have to calculate a t-test. For the t-test, we need standard error, and standard error is s over square root of n. So in this case, 2.69 over sample of 20 words. And so our standard error is 0.062. Now we can calculate our t-score, y bar minus mu naught over SE. So 5.5 minus the hypothesized value of 6.5 over the standard error of 0.602, and that gives us a t-score of negative 1.66. Also, because we're working with t, we need to calculate degrees of freedom. That's just one less than the sample size. But what this tells us now is our reference distribution is a t distribution with 19 degrees of freedom. Our alternative said not equal to. That's also very important here, because if it's not equal to, you actually end up having to calculate the part of the curve corresponding to the two different tails. On the one side, you'll have the negative of the value that you calculated, and on the other side, you'll have the positive of the value that you've calculated. The good news is, because of symmetry, if you just calculate one of the tails, you automatically know what the other tail is. So in this case, that translates to, we can use our t calculator to find the probability that a t distribution with 19 degrees of freedom is less than or equal to negative 1.66. You're going to go to that t calculator. You're going to enter 19 degrees of freedom You're going to enter a t-score of -1.66. Make sure the probability field is clear. Hit calculate, and this is 0.057 if I round to 3 decimals. So that corresponds to one of the tails, but because the t-distribution is symmetric, the other tail has to be exactly the same. So my p-value is 2 times the 0.057 because it's both tails, since my alternative in this case was non-directional. And so that means that my p-value is 11.4%. I'm comparing that to an 8% evidence threshold. So my p-value of 11.4%, how does that compare to my level of significance? Well, it's greater than. So this would be considered a large p-value because it's larger than my significance level. And that means there's a large chance that the null hypothesis is true, so I do not reject the null hypothesis. If I do not reject the null hypothesis, this is now what I assume to be true. So my sample evidence suggests, yes, the editors did achieve their goal because the sample evidence is consistent with the average being 6.5 letters per word. So that, I would say, is a good outcome for the editors in this case. Now, I know there's one more example, but we're coming up on the threshold of how long I tried to keep these sessions. So I'm going to reserve the last example problem for our live session on Thursday. So there'll be one more video tomorrow, lecture video for you to watch. Thursday, we will have a live session, and on Thursday, we'll also talk about the test content.